Hi all, thanks for tuning in to my another video of paper reviewing. Today we will take a look at the paper called Reparameteizable Subset Sampling via Continuous Relaxation by Michael Xie and Stefano Ermo from Stanford University. So if you remember our last paper reviewed in the week before last week, we basically talk about how to discretely sample some of the subset from a total set. In that paper, each entity to be selected is assigned by a distribution called Kumaraswamy distribution, and then we select them individually and independently. So what about I tell you that our mission is to select a k feature subset from the in total n features. To solve this question, an intuitive thought is to find out the distribution of each subset or each possible subset and sample from this distribution. Well, the problem is to finding out this distribution over every possible subset is intractable, because the degree of freedom of such distribution is the number or the possibility of selecting k from n minus 1, which is the fractal of n divided by the fractal of n minus k divided by the k fractal and minus 1, which is too high and intractable. We couldn't even represent such model using some parameters. But there is a miracle algorithm solved exactly this question. It's called weighted reservoir sampling. This is the exact algorithm this paper is started from. I assume that maybe most of us has known about a little bit about its cousin, reservoir sampling. The reservoir sampling has two variations. Both of them solve the same question: sample a subset in size of S from a total stream or a whole subset of n entities. The weighted reservoir sampling does exactly the same: sample S entities from in total n entities, but for each entity, it is assigned with a weight, which indicates its probability of being selected or being sampled in this sampling process. So the probability of each individual entities being sampled is represented by this formula right here. The intuition behind the reservoir sampling is as such: for each iteration, we sample one instance from this in total n instances without replacement. For instance, for the first round, we sample an instance corresponding to the weight, say Wi1. Then this probability of sampling this I1 entity is Wi1 over z, where the z is the sum of all of the weights, which is the partition function. Then without replacement, then the weight of I1 is subtracted from the partition function z. Therefore, this denominator has z minus Wi1. Then we go into the second round. In the second round, the probability of sampling, say, I2 is proportional to Wi2. Then Wi2 divided by partition function in this round, which is z minus Wi1. Probability of sampling I2 in the second round is Wi2 divided by z minus Wi1, and so on and so forth. Therefore, sampling a whole sequence from I1 to Ik is written at first formula. So it was first introduced in 2007 by Ephraimides and Spirakis. The weighted reservoir sampling basically does solve this exact subsample problem with respect to the distribution that we mentioned before. So the main algorithm is listed in the paper as the algorithm 1. It's called the weighted reservoir sampling non-stripping version. The foundation of this weighted reservoir sampling algorithm is in the algorithm 1. It's based on two foundations. The first of them is the inverse transform theory, and the second is the I don't know exact name of it, but this is related to the extreme value theory, which we could see on the top K part. But let's start with inverse transformation theory. This inverse transformation theory basically guaranteed that we could basically sample from any distribution which has a continuous support set by at first sample a random seed, so-called random seed UI, denoted in this algorithm, with respect to the uniform distribution between 0 and 1. Then we can transform this random seed UI through this inverted cumulative distribution function, or the CDF. Then specifically in this with weighted reservoir sampling, this transformed seed is called R, and based on the paper from Ephraimidis and Pirakis from 2006, we could for each round generate one such random sample, which is called RI here, and then sorted the whole RI sequence and then select the top K. This top K selection is in the same distribution as we mentioned before, as we mentioned in the Formula 1. Also in the paper, it is also introduced the Campbell-Max trick could do the same. These two are mathematically equivalent. If you do the research on the internet, you could find the proof that those two are mathematically equivalent with respect to the sampling. And the author also gave the proof that those two are mathematically sampling with respect to the monotonic transformation, because we only interested on the top K or the order of the final score R's. But unfortunately, in the paper, the author then didn't mention why did they choose the Campbell-Max trick instead of, or the weighted reservoir sampling. So I could guess two of the reasons why did they choose that. The one reason is that there are two negative logs in the Campbell-Max trick, which could somehow mitigate those gradients that occurs in the training, which could prevent the gradient explosion. Or they're just trying to simply keep consistent with the reference, which is also mentioned in the 2017 paper from Madison. It's called the concrete distribution, continuous relaxation of discrete random variables. In this paper, it is also used the Campbell-Max trick from beginning to the end. So maybe those authors just want to try to keep the consistent with those references so that they could use the same theoretical or mathematical foundation. And because this weighted reservoir sampling and Campbell-Max trick are both differentiable, so that they could both be embedded into a deep neural network. So honestly, I don't know why do they choose one prefer than another. Well, in order to use the Campbell-Max trick or the weighted reservoir sampling, we have three questions to solve. The first question is that what is the probability of sampling a subset? Because this is basically the problem that we have to counter. The second question is, how do we generate a differentiable key to sort for either Campbell-Max trick or the weighted reservoir sampling? Anyways, we have to embed the sampling algorithm into a deep neural model, which is optimized by the gradient-based optimization algorithm. The third problem is that basically the same. What is the differentiable top K selection? Anyway, I could not even think of less differentiable operation than the top K selection, or selecting some of the indices from a total set. So let's take a look at those three sub-questions one by one. The first question, what is the probability of sampling a subset? Yeah, you haven't heard it wrong. I just mentioned the weighted reservoir sampling or the gamma max trick are sample a sequence of the subset from the total set, because every output of either algorithm is actually a permutation of this selected subset. We do not even interested in the order within the subset that we sampled out. How should we then average the distribution of all of the permutation of selected subsamples? Well, saying of the averaging them out, this is where Monte Carlo takes place. We just sample those sequence as is, because each permutation of the subsets just occur according to the distribution of the permutation, and we calculate the sum or the expectation of the final score. Then if we use those sets as if they do not have an order, then we will get is an estimation of the selecting the subset simply by doing the expectation over all the permutation, as mentioned in the second formula in the paper. And about the second problem, the generating a key of sorting, which is also differentiable. Well, fortunately, those R's in weighted reservoir sampling and the gamma max trick are differentiable, and because this gamma max trick is basically a monotonic mapping from the weighted reservoir sampling, they are mathematically equivalent. But unfortunately, the author did not mention why do they prefer the gamma max extension instead of rather than the weighted reservoir sampling. Speaking of the third problem that we have to counter with, is the differentiable top case selection. So in this paper, those authors use the soft top case selection introduced by the Prutz and Roth in 2018 from the paper called Neural Nearest Neighbor Networks, which, well, as we all maybe expect, when selecting the nearest neighbor of a point in the matrix space, we have to sort every other points, or based on the integral of matrices between each pair of those points. This is where this top case selection is happening in the nearest neighbor selection. When this is trained in the neural network, then we have to find the differentiable way of selecting this top K. So this algorithm of selecting the top K is implemented iteratively, and so as we could see from the formula 3, 4, and 5, each transformation is differentiable, and in each iteration we basically generate a P of Aij equals 1, which is the expectation of selecting the ith instance at the j step, because we have to select in total j equals to 1 to k sub-instances from n instances. So the intuition of this selection is like that. We at first select one instance from the total set based on the weight and also according to this distribution. And after selecting this instance, we set those weight into minus infinity, because if the softmax in the formula 4 is replaced by the real max, then the probability of Aij, if they selected, is 1. Then the 1 minus P of Aij equals 1 in the fifth formula is 0 already. Then the log of 0 is minus infinity. So in the j plus 1 round, the probability of selecting I is 0, because this alpha ij plus 1 is minus infinity right now, and in the softmax or in the real max, the probability of selecting the ith instance is 0. And this soft top k operation basically controlled by the parameter called temperature, aka this T in the formula 4. T is larger, the distribution is well, a little bit smoother than the real max, because this is basically a expression of softmax. When the T is smaller and smaller, and when the T approaches to 0, this softmax degenerates to the real max, which selects the largest alpha IHA. It is also proved in the paper that when T is larger or equal than 1, this softmax transformation, or the soft top K transformation, it gives the same results as the original top K1. But there's another problem. This soft top K, or especially the softmax used in the soft top K, has the intuition that when T approaches to 0, this whole thing degenerates to the top K, or this real max. But it is also proved here that when T is larger than 1, this keeping order feature is preserved. Then what does it happen between 0 and 1? The author just simply suggests that we shouldn't choose a T that is between 0 and 1 because it doesn't preserve the order. But do you use some features like T approaches to 0 and then it degenerates to the real top K? There must be a sudden change at the point T equals to 0. So it really understudied how this parameter T will affect the result of selecting the top K if the T is larger than 0 and smaller than 1, which, in my opinion, causes a contradictory when you're trying to say that, well, this soft top K approaches to the top K when the T approaches to 0, but you cannot use the value of T between 0 and 1. This is a bit tricky. There is a better way of selecting the top K, so I will put another paper that proposes of soft selecting the top K based on the transformation theory. So intuitively, what this transformation theory-based selecting top K consider that the weight of each instances is a pile of dirt, and the pile of dirt has its weight, and they are assigned or sorted on the axis of number according to their weight. And there are K plus 1 bucket. There are 2 buckets. One bucket is called selection, which has a volume of K, pile of dirt, and another bucket is called depletion, which has a volume of n minus K, pile of dirt. Then they minimize the transformation cost from those unsorted pile of dirt to those 2 buckets, one for the selection and one for throwing away. The piles of dirt in the selection bucket is the final result. Because we have to keep this transformation function or the transformation matrix differentiable, therefore we have to make sure that the transformation matrix should have a corresponding Jacobian matrix. Therefore, this whole optimal transportation theory based algorithm is, well, using gradient optimizable. I think this could be a better solution to the soft K algorithm, since there seems to be a paradox in this differentiable top K procedure in the paper that we introduced today.